Welcome back, guys. So let's start our next lecture. So today we'll try to stabilize our device. And what's the need of that? Because still now what we are doing, we are assuming that our device is already stable, or if it's not stable, then what we are doing, we are doing conditional stability design. But if there are some situation, if we need to do a unconditional stable amplifier design, then is there any way? So today we will answer that question. So let's start. So to design an unconditional amplifier, this is our flow diagram. What we'll do, we'll same as before, we'll do the stability analysis, and for that we know already what are the procedure, and we will ask ourselves, is it an unconditional stable device? If it is not, then what we'll do, we will try to stabilize it. Actually, till now we are not covering this section of our amplifier design, and what we are doing, we are bypassing to our selecting gamma s and gamma l, because what we are assuming that we will design it for a conditional stable amplifier, or we are assuming that our device is already stable. But in practical scenario, our device in 90% or 95% time, our device won't be stable. So we need to stabilize our design if we need to design it for a unconditional stable amplifier. So let's proceed. So what are the way? So we have actually two way. We have a using a resistive loading way, and we can also do it using a negative feedback technique. But in today's lecture, I will cover largely how to stabilize our amplifier circuit using a resistive loading. And in some other video, I will take up this negative feedback one. So we know that everything has a price. Like we are stabilizing it, or we are forcing it to be a stable, unconditional stable device. That means we need to give some price for that. And what are those prices? They are, if we stabilize it, then it will reduce our power gain. I will show you in one practical example. It will degrade our noise figure, and it is in common sense, like we are using a resistive loading technique, so we are using some extra resistor, and noise are directly proportional, actually not noise, thermal noise are directly proportional to the resistor use, or how many resistor are there. So that means our noise figure will increase, and also there would be a degradation is in VSWR. So if we are ready to give this price, then we can design an unconditional stable amplifier design. But actually what we do, we design unconditional stable amplifier only when we do it for broadband amplifier design. In narrow band, as the frequency range would be a very narrow part, so we can go with a conditional amplifier design, because otherwise we need to pay these prices. So from our last lecture, we already know when our amplifier would be a unstable region, like when it will be a unstabilized amplifier circuit, and those things when our gamma in would be greater than 1 or gamma out greater than 1. Okay, but we have some technique. You can read this statement. Even when we select gamma and gamma s, which produce gamma in and gamma out, we can recall this formula here, because our gamma in and gamma out directly come out from gamma L and gamma S, and our main objective of any amplifier design is to select gamma L or gamma S. So if we select some gamma L and gamma S, and if they result in gamma in magnitude more than 1 and gamma out magnitude more than 1, then we know it would be a unstabilized amplifier design. But we can still stabilize it, and for that what we need to do, the circuit can be made stable if real part of total input and total output loop resistance is positive. So actually what I have did, I have highlighted and make the big sizes those keywords. Okay, uh, and in this video I'll try to answer or simplify this keyword. And actually we have many mathematical derivation for this whole statement, but in this video what I'll do, I'll go graphically, like I'll make you understand graphically how this statement is true. So in simple sentence, what it is saying, it is saying our real part, and it is saying loop resistance. So if we see this figure, loop resistance in input part, so it will be Zs plus Zin. This is the loop resistance in input part, and in output part it will be same ZL plus Zout. So our real, why real? There are mathematical explanation, but in this video I'll show you with graphical representation why it is real, why not imaginary. I'll give you an answer, just wait. So this is the part, and why it should be positive. In my previous video, in some few video, I have already explained why our input resistance need to be positive. And actually any amplifier, why it amplify? Because it has some negative resistance in it, and negative resistance imply the reflection coefficient will be more than 1. That means it will amplify my reflecting signal. And if my gamma in is more than 1, then you can see like my reflected signal will grow and grow, and which will result a oscillating device, and that's why we say that it is not a stabilized device. So you just see my previous video, there I have already explained why it need to be positive. So to make our journey easy, let's take one example. Here are the specification I have taken directly from the book which I am following. And what are the specification? We have given with one MOSFET which need to be operate on 800 megahertz, and I have this as parameter already we have given. So we know what are our step. Let me revise. Our step is to first see if it is unconditionally stable or not. If it is unconditionally stable, then video is finished here. We don't need to do anything. But it won't be an unconditional stable device, and then I'll try to stabilize it, and that's my topic for today's video. So step 1 is stability analysis, and stability analysis we already know, I have already covered that for stability analysis our K need to be greater than 1, and it is not or, mind it, okay? And the magnitude of my delta should be less than 1 if I am correct. And we have one simple formula which is given by mu, and that also I have covered. If mu is more than 1, then it is sufficient and necessary condition for my device to be stable. So what we can do? We have given with S parameter, we know the formula of K, delta and mu. We can use our scientific calculator, we can calculate it, we can find it out, but we are engineers, right? So we want any problem to be solved as quickly as possible. So that's why I don't encourage you to use calculator for this much of big calculation. And what I use alternatively, I use MATLAB. So I have already written one script on MATLAB, and don't worry, I'll give that script on my description, but I strongly recommend you don't see that file. You try to build that script on your own. Yeah. So this is my script, and you can see first paragraph. You can see in first paragraph, you can follow my cursor. In first paragraph, what I did, I have just entered the S parameter which are already given in my question. Then I wrote the formula for delta, simple formula here, nothing complicated. Then what I did, I find out, because here in this line my delta will be in complex form, but I need the magnitude of my delta. So in this line I am getting that magnitude, then I am printing it. Then next is the formula for K, then I'm printing it, then the mu, same formula I'm printing it, and after that the below things I'll come little later. Okay, but let's see what is my k, mu and my delta to confirm that our device is unstable. So let's run it. Yeah, it's done. And see, magnitude of my delta is less than 1. Perfect, we need that. K is not more than 1 and my mu is also not more than 1. That means we got the confirmation that our device is not stable. So we need to stabilize it, because without stabilizing also we can go to design part, but then our design would be a conditional stable device. But as our employer or the customer has asked us to design it for unconditional stable device, that's why we need to stabilize it. So let's go to that part. Device is not stable, so that means we need to draw our stability circle, the input and output stability circle. And for that, drawing any circle, what we need the coordinate for center and the radius. We have those formula how to calculate the coordinate of center and radius. And same thing again, we'll use our MATLAB. And here in MATLAB I have already calculated those, and they are as in the screen. You can just refer as in the screen. So what we can do now, if we don't have access to ADS and we have only access to Serenade, and I don't know how to draw the stability circle in Serenade. If you know, you can comment it out, it will help other, but I don't know how to do it in Serenade. And if you don't have ADS, then what you can do, you can do it manually. You can just take one Smith chart and we have the points, and we can draw the circle, and after drawing the circle, then the next step I'll just discuss. But as I have the access to ADS, I'll show you in the ADS, like, because I can also draw it manually, but it will take time. So what I am doing, I am taking help of ADS. So what we need a SNP box, then we need to feed the S parameter file. I have already made the S parameter file, and I have already explained how to make S parameter file. So here I am not explaining everything again to save our valuable time. Yeah, and it is a touchstone, and you can view also. I have selected wrong. Yeah, and we can view also our S parameter. So, and it is of 2 port. Okay, then we need to get the termination, where I'm not telling everything what I am doing, because I'm assuming you already know these things, because I have already explained those things. As parameter, then get one simulator here, and simulator should be a single point simulator, because we have only one point, and that is 800 megahertz, and select it to 0.8 gigahertz. Then what we need to see the circles, stability circles. So this is my input stability circle, and this is my output stability circle, and we also want to see the mu to get to know if, like, I have already confirmed you that it is not stable, but still let's see if ADS is coinciding with our result or not. So I am selecting mu again, and then I think I have taken everything. Let's run it, and results are here. So let's see first mu, and yes, it is well below 1, so it got confirmed. And our main concern is to see the circles. So one circle and another circle, add and OK. And it is not our ordinary Smith chart, so we need to adjust the scales. It should be up to 1. So this is your stability circles. Blue one is input and red one is your output. And why what? So why we are drawing these circles? Because in next step we will select our gamma S and gamma L, and those gamma S and gamma L should not be in unstable region, and our stable region is outside of this circle for gamma S and outside of this red circle for gamma L. Why outside? I already explained. So please revise my previous video. So roughly we have one circle here and another circle here, and we don't want to select our gamma S here and gamma L here. That means there should be some mechanism or something which will confirm that if we select any gamma S, it will be outside of this region. Perfect. So what we do for that? Let me draw my, this is my gamma S, correct? This is my gamma in. Now see one thing, this red circle are for impedance and blue circles are for admittance. So if anyhow I confined myself in this circle, so now if we add one resistor here, then we will have one new gamma S dash. And what is our gamma S? Gamma S will give me some value of Zs, which will be in the form of x plus j y in our Smith chart. And our aim is to confine ourselves in this circle only, because we don't want to cross ourselves in this unstable region. Okay, and this circle is some real part of my Zs, and real part of Zs, which imply I'll get some gamma S, and my main concern is to select gamma S. So for example, this circle will result 9 ohm resistance, because this circle have some number, like it have 0.1, and we know it is normalized, so 0.1 into 50 will be 5 ohm. So this circle is my 5 ohm. Perfect. So let us add one 5 ohm resistor here. So if I add one 5 ohm resistor here, then any new gamma S here will have a real part more than 5 ohm. And why it is important to have a more than 5 ohm? Because other circle, red circle, which are crossing this unstable region are less than 0.1. For example, this circle, it is 0.2. 0.2 into 50, 10 ohm. 0.3 into 50, 15 ohm. That means after adding this 5 ohm resistor, any new gamma S which we are seeing will be for definitely more than 5 ohm. And more than 5 ohm means we are pushing it in the stable region. We are pushing our new gamma s in the stable region, and here it is clear why it is real, because this circle is the real circle part, and these are the reactant part, and reactant part could be anything, no issue, till the time we are confining us in the 5 ohm circle. So I hope I have cleared the reason why it is real part, like why in the statement they have written real part. Okay, that's the actual reason. There are mathematical explanation, and you can get ample of resources in the internet, and I am not discussing those things again here, but for easy understanding and how I understood this thing, I have explained here. Same way, what we can choose, we can choose, instead of a series resistance, we can choose one, let me yeah, one shunt resistor, and we'll get a new gamma s. And we know in Smith chart, if anything in the shunt connection, we use our admittance chart, correct? So we will use our blue chart, so we will see which blue chart is touching the unstable circuit, stability circle. So roughly this blue circle, if I choose this blue circle or any other blue circle, they will go in my unstable region. Okay, and in blue circle also you can see this way the value of blue circle are decreasing, and this way value of blue circle are increasing, and value of blue circle are nothing but my admittance, and if admittance is increasing, resistance or impedance will reduce. So that means if I go in this side, my resistance will increase, and if I go in this side, my resistance will decrease. Perfect. So what we want to see, we want to see a resistance which should be lower than this circle, and in shunt connection of my resistance, if a resistance is of 50 ohm, then I can add ample of resistance in my shunt, but I can't go more than 50 ohm. It will be always less than 50 ohm only, and that's the reason which explain why when we use a shunt resistance, our gamma s will be forced to be coincide in this side only, and it won't go this side, because if it go in this side, we can any blue circle, because we are seeing on the real part of admittance or impedance. So if we choose this circle, then here we are in stable region, but any reactance, because these are the reactance circle, any reactance can push it to the unstable region. So better to confine ourselves in this circle only, so any reactant value won't disturb our stability. I think you got the point. Same thing is valid for output stability, and there also we can use a series or not end, or a shunt resistance, and these are, you don't need to do it in precisely, you just need to assume one, because in modern circuit design like ADS we have the optimizer. We can see our optimizer in action to see if the selected resistance making our device stable or not. So in our example here, we have for input part, it is around 0.186, like this circle we need to confine ourselves in this part, and this circle is around 0.18 roughly we need to take. Okay, and 0.18 means 0.18 into 50, it is 9 ohm if I'm correct, and 9 ohm is for the series if we want to add one series resistor, and for output part it would be around 55, yeah, 0.55, or roughly, like I have already calculated it, it will be around 26 ohm. So I can use one 9 ohm in the input part and one 26 ohm in the output part for the stability, and I'll show you here just now. But if you want the shunt connection, and for shunt connection what I need the admittance chart also, and you can um, do it by this thing. You need to go to import option and in coordinate add both and click OK. See, red one is your admittance chart. Still our pointer are giving impedance here. Okay, so you can again change it. How you can change it? You need to click here 2 times, and in format in type you can write admittance, so it will change to admittance. That means I am getting 0.51. I want any circle less than 0.51. I want to push my gamma s in this region from here to here 0.51, and it will not into, it will be 0.51 divided by 50, and that would be your shunt resistance in input side. So shunt part is your homework, you can do it. I'll show you for the series one. I'll prove it here. So what I'll do, I'll disable this, I'll bring to register, and what are the value? One should be 9 ohm and another should be 26 ohm. You calculate it yourself, you'll get the same value. And then what we want to see, we want to see our mu should be more than 1. So let me plot the mu, and yeah, it is more than 1. Let's see what happened to our stability circles. They should be out of my Smith chart, and yes, they are out of my Smith chart. Why? Because this is your Smith chart. Your Smith chart should lie in 1 only. So see, in Smith chart you can't see those stability circle. That means your full Smith chart is your gamma s and gamma l. You can choose any one, no issue. Let me show you one thing more. Like in the starting of my video I have said like gain will get compromised. So let me see what's the gain now. S21 dVn1, yeah. So I am getting a gain of around 12.35. Let me turn on my history. Yeah, let me disable this. I'm shorting them. Okay, and now let me run it again and see. This blue or black is without a register when my device is not stable, unconditionally stable, and then I am having a higher gain than when I have the uh, I have done the stability techniques. So that got proved here. So that's all for today. In my next video I'll take up the bilateral design, or I'll go for figure of merit for unilateral design. So thanks for your time. If you got some uh, knowledge from this session, please subscribe to my channel. It will motivate me to make more and more video. Thank you.